Okay. So collisions. So this is a class diagram. For the most part, it stayed the same. A couple additions. For example, uh, each collidable now has two collision volumes, one being the actual collision volume that the user chose for that object, along with a default collision sphere, which is used later during the collision testing. I'll talk more about that later. Um, yeah, the test pairs. I'm gonna talk more about that later. Um, and aside from that, the collision volume. So now there's a B sphere, but now there's also the AABB and the OBB. Um, yeah. So looking into the new collision volume class. So it's a no, that's not it. This one, nope. Here we go. Okay. So the collision volume parent class, it's purely abstract. Uh, so I have these abstract methods that are used that utilize the visitor pattern to call the proper intersect methods on the correct collision volume pairs. Um, so each of the specific collision volumes have to explicitly define the accept, and the visits. Um, and yeah, so let me just go into ABB. So actually, I'll start by trying to explain the visitor pattern. So, so I, yes, no, that's self. Yeah, yeah. Okay. Okay. So intersect is called onto collidables. Uh, then math tools then extracts those. Nope, it's in here somewhere. It extracts the actual collision volumes and then calls intersect accept on the first collision volume. So, um, so as I mentioned, each volume has to explicitly define this, but so what happens is it calls the intersect visit of the other collision volume and passes itself in, and then this will then actually call the correct, well, at that point it can decipher exactly what the two volumes are, and then with that it knows which intersect method to use for those two volumes. So yeah, if it's an AABB and an AABB, then I'll go to this intersect. Um, so yeah, that's the visitor pattern. So back to the AABB, just what's it storing and how's it getting its data. Here we are. Okay. So AABB, so in its compute data, it gets its minimum and maximum point by grabbing the array of vertices from the model, putting them into world space, and then just comparing them all in order to get the minimum point and the maximum point. So along with that, I'm also storing my half diagonal and my center point. Um, that's specifically for testing AABBs against OBBs. Um, yeah. So that's AABB. I think that's it. OBB. Um, so for compute data, I'm just grabbing the min and maximum point of the local collision volume. Um, Yeah, and then I'm just getting my half diagonal and center from those 2 points. Um, so as for the actual intersects with the two new volumes, AABB, actually I can go to the math tools. So against so all of the pairwise collisions are explicitly defined inside of the math tools. For AABB in the sphere, I do a clamp test to see if the distance of the center point and the to see if the B sphere collides with the AABB. I do something similar for OBB, except I put the sphere into local space of the OBB. ABB versus ABB, I just do an interval test on their min and their max. ABB and OBB, I have to do I have to use the separating axis theorem. So this is how the center and the half diagonal of the ABB come into play. I have to use those along with the OBB's center and half diagonal, and test to see if their axes are overlapping. Yeah. And then OBB versus OBB, same thing, separating axis theorem. So yeah. So that's it for my volumes. Changes to my collision commands, test commands, and yeah, I'll start with that. So I broke my test commands into, I'll start with test pair. I broke them into tiered collisions. So first thing I do is so now every collidable group has its own AABB, which encapsulates all the objects that belong to that group. So then I test the collidable groups AABBs against each other to see if they're colliding. If they're not colliding, then that means that none of the objects of either group could possibly be colliding, so there's no need to run any further tests, so I bail out right there. If, however, the two groups AABBs do collide, then I do I test the B-spheres of each of the collidables in both the groups. So this is how the default B-sphere on the collidable comes into play. So as I previously mentioned, all of the collidables now have a default B-sphere. B-sphere intersection tests are fairly cheap, so honestly it's a lot better to do a bunch of B-sphere tests compared to doing a bunch of OBBs, ABB tests. So yeah, so this just keeps light testing. So if intersection is detected between two objects, B-spheres, then it does the test on the actual collisions. And then it tests their actual volumes, whatever those are, and then it'll call the collidables collision method for both of the collidables if detection is detected with their actual volumes. So yeah, this is test pair collision. I talk about terrain in my terrain video. This is test self. Since all the objects in test self belong to the same group, you can't really test their AABBs, the group's AABBs. So you just have to go straight into testing their B spheres, and then same thing like test pair. If their B spheres collide, then test their actual volumes. Okay, yeah, so that's collision test, the collision test commands. So now the changes to collidable group. So as I mentioned, collidable group now has its own AABB and min and max, which I use to calculate the AABB, but yeah. So yeah, so what happens is prior to running the test commands I call compute group boxes, which then I believe I have a command connecting the two, the collidable group and the collision manager. So then it'll call execute compute box on the command. Yeah, it's a command. And then this will compute the group AABBs for each of the collidable groups. So I'll just go to that. So execute compute group box, which, and then this actually calls compute group box on the collidable group. So just to mention, like this never is used anywhere. I got rid of whatever I was using that for a while ago, but I didn't didn't get rid of that. But anyways, back to actually computing the AABB for the group. So then the group will then iterate through its collection of collidables. It'll grab their B-spheres, use those B-spheres to get min and max points, and then just test all of their min and max points to extract the min and the max for the group. And then it'll compute the actual AABB using those min and max points. Okay, so just a quick demo. Come on. Okay, so I have Okay, I have an enemy and my player tank. So these blue boxes are their collidable group AABBs. If they intersect, then it'll go into testing their B-spheres. So if their B-spheres intersect, then it'll go into testing their actual collision volumes. So it's a little hard to see given the orientation of the enemy. So yeah, they're B-spheres, and now their actual collision volumes aren't intersecting. But if I move a little closer, I can actually, so now I'm actually intersecting with the enemy. And then just to test out a couple models, so I have my B-sphere and then I have my OBB. Okay. And yeah, I believe that's it for collisions.